Hey, you came back. You must be a glutton for punishment. In this video, we'll be covering section 1.2, entitled Data and Sampling. We'll be talking more about different types of data, in particular, we'll be breaking down the two types of quantitative data. And then we're going to get into the different sampling methods that you can use in order to gather data. So recall that quantitative data is data that's kind of mathematical. With quantitative data, you can find things like averages and differences and make sense of them. They quantify things. And we're going to further subdivide quantitative data into two different categories. The two categories of quantitative data are discrete and continuous. Discrete data is data that can take on a countable number of values. In other words, there are gaps between possible values. The term countable number is actually a high-level math idea. It turns out that there are different sizes of infinity, and I'm not going to get into all that, but kind of the smallest size of infinity is the countable size. If a set is countable, it's either finite, it ends somewhere, or it's kind of the smallest size of infinity. Because that's so technical, I prefer what you see in parentheses there as our definition. If there are gaps between the possible values of the variable, we're going to say the variable is discrete. So if the variable has to take on a whole number value, it can be a whole number but it's not allowed to be a decimal, then that variable is going to be discrete. Or if it can take on a decimal but only a certain number of decimal places, like money. In American money, you can go as far as 2 decimal places. If you're going to be a jerk about it and talk about gas pumps, I guess those go out to mils, which is the 3rd decimal place. But as far as money in your pocket, money in your bank account, that only goes out to 2 decimal places, and so there are gaps between the possible values. That would be discrete. On the flip side, we've got continuous data. Continuous data is data for which there are uncountably many possible values. That is, there are no gaps, assuming a fine enough measurement can be made. So I'm not going to go into detail here, and I'm not going to say it exactly correct, but basically uncountable means bigger than that smallest size of infinity. If there's more than countable, then it's uncountable. And again, that's kind of technical, so rather than doing that, we'll just look at the parenthetical part. It says no gaps, assuming a fine enough measurement can be made. A standard example of this might be weight, for instance. Right? So if you're weighing something, you might say an object weighs 10 pounds, but you're probably rounding that to the nearest pound. If you were to go for a little more accuracy, maybe it weighs 10.2 pounds. And if you take that a little bit further, 10.24 pounds. Maybe take that a little bit further, maybe it's actually 10.237 pounds, and that 7 just rounded up to a 4 on your scale. So as long as you had an instrument that was delicate enough to measure at your level of accuracy, you could keep adding decimal places. That's basically what continuous is. So discrete has gaps, continuous has no gaps. And I'm going to go into some specific examples of this here in a second. But before I do that, I want to talk just a moment about why we would care. When we get into the unit where we cover probability, Unit 2, we're going to talk about discrete random variables and continuous random variables. And the math that we do for those is a little bit different. The discrete things tend to be a little bit easier because of the limited options. Continuous tends to be a little more difficult and often requires calculus, which is one of the reasons why you had to buy that calculator for this class, is so that the calculator can knock out the calculus that we don't know how to do, and then we can interpret the results. So now we have a little bit of motivation for why we want to be able to distinguish between these later. Let's look at some examples. So I've made up 4 examples here. The first one says the amount of credit card debt. First off, that's definitely a quantitative variable, but we want to take it further. Is that discrete or is it continuous? Well, the amount of money that you owe is limited. There are gaps between the possible values. You might owe $2,000.10 and you might owe $2,000.11, but you can't owe anything in between that because our money system doesn't work that way. And because there are gaps between the possible values, this is discrete. The next example says height measured in inches, and you'll notice I obnoxiously underlined measured there. The height of something is a one-dimensional measurement of distance, and given an appropriate tool, you could obtain a finer and finer measurement. There are no gaps between the possible values of the height of something. This is continuous. Now there are 2 more examples here, but let me pause for a second and talk about one more way that you can distinguish between these. I'm going to pop back to the previous slide for just a second and throw these in here. With discrete data, because there are gaps, you can find yourself counting in order to find these things. I know I used the word countable here, but I'm going to repeat up here that discrete variables are usually counted. Like you can count money. In the credit card example, we said that the amount of credit card debt that you have is a discrete variable. And yeah, that's because there are gaps between the possible values, but you might also think of it as, well, the amount of money that you owe could be counted. You could count it out, and so that's discrete. Continuous variables tend to be measured. They come from measurements. So weight is measured. Distances are measured. If it comes from a measurement, then it's continuous. If it comes from counting, it's discrete. You might not think of all continuous variables as being measured, but in a sense they can be. This next example illustrates that, not to give the answer away. The third example here says the number of seconds needed to complete a 100-meter dash. The time in which it takes you to complete a race is a measurement. Now, you might not think of time as being measured, but you do measure time. You measure time in seconds, or in years, or in decades, or in centuries. An amount of time is measured, and because it's measured, this is continuous. Or you might go with the more formal explanation. There are no gaps between the possible values. A really fast runner might run a 100-meter dash in 10.2 seconds. If we were to use a timer that was a little bit more accurate, we might find out that they ran it in 10.19 seconds. And if we took that measurement a little bit further, it might actually be 10.193 seconds, and so on and so forth. We could keep measuring out a higher and higher degree of accuracy. There are no gaps between the possible values. This variable is continuous. Whether you want to use that formal argument or just simply say that time is measured, this is a continuous variable. Last one, the number of cousins you have. Okay, so two arguments here again. The less formal argument, you could go through and in your head list all of your cousins and count them out one at a time. This is something that you can count. By that argument, this is discrete. Or you can use the more formal argument. We said that discrete variables have gaps between the possible values. And the number of cousins you have definitely has gaps between the possible values. You might have 8 cousins. You might have 9 cousins. I hope you don't have 8.7 cousins. I don't even know what that would mean. If you have you can't have a fraction of a cousin. The whole concept of a fraction of a cousin is horrifying. The number of cousins you have should be a whole number. That makes this discrete because there are gaps between the possible values. Again, we won't use this distinction much in the near future. Not that we won't run into discrete and continuous variables, but we'll have very little reason to label them as such. The difference between discrete and continuous will become much more important when we get into the probability unit. There'll be an entire chapter on discrete random variables, and then the book actually has multiple chapters on continuous random variables, but we're only going to hit up one of those. The second part of this section deals with sampling methods, how we gather the data. Whether the data is quantitative or categorical, whether you've got quantitative data and it's continuous or discrete, the method in which you gather the data can matter. So we'll talk about a few of the different ways that data can be gathered. Different sampling methods. The first is the best from a mathematical standpoint. I'm not saying it's the most convenient, but mathematically, a simple random sample is the best kind of sample that you can have. A simple random sample is a sample selected in a way such that every possible sample of the same size has an equal chance of being chosen. In a simple random sample, you've designed your sampling method in such a way that not just every individual has the same chance of being selected, but every group of an equal size has the same chance of being selected. The method for doing this is very straightforward. You give every individual their own label, like you might enumerate the entire population, give every individual a number, and then you use some sort of random number generator to select the individuals. So your calculator has a random number generator. You can get a random number generator from a computer. These are mathematically best because if every group has the exact same chance of being selected, then we don't have to worry about norming out the differences between the probability that one individual or one group gets selected over another. That's been completely wiped out. Makes the math easier. If that's the case, then you might wonder why any other sampling methods exist. Why wouldn't we always just use a simple random sample? Well, where it's easy to describe, it can often be difficult to pull off in real life. You can't get a true simple random sample of the entire United States population. It's just way too large. Or you might be in a situation where you don't have access to the entire population, so it's impossible to enumerate them. Like if you're studying some unknown species, you're in some rainforest and you're looking at some species of ant. You can't enumerate all of the ants because you can't track them down. That's impossible. You just can't pull off a simple random sample in that case. So while simple random samples are mathematically best, they're not always convenient, and so there are other sampling methods. Some of the other sampling methods are easier to pull off, and some are better than others, but we're just going to discuss them. The second sampling method the authors bring up is what's known as a stratified sample. A stratified sample is a sample selected by dividing the population into groups, which we call strata, and then selecting individuals from each group. The singular of strata is stratum. So you divide the population up into many strata, and then you select some individuals from each stratum. In the text, it says you want to select a proportional number from each. Other authors would say that that's not required of a stratified sample, and if you do that, we call it a proportional sample, but it doesn't really matter to us. A stratified sample is basically where you break up the population, and then you select a few individuals from each of those groups. As an example, suppose I took my student population and I divided it up by class, right? So I'm going to draw a big circle for my population, and I'm going to put and divide it up. Let's say I have 4 classes in a semester, and I'm going to put a few students in each. The students are X's. Maybe some classes are bigger than others. And I'm going to do a stratified sample of this population. Well, I would randomly select maybe 2 individuals from here. And what I just did there, by the way, was not random. What I did was haphazard. I chose those without thinking, but that's not random. If I truly wanted to do this randomly, I would use some kind of random number generator to select between those. So what I'm doing here isn't random. Maybe I take 3 from here. It's a bigger group. I'll take 2 from here. And I'll take just 1 from here. And the ones that I circled and put those arrows, I'm dragging them out and making them my sample. Notice that I selected a few from every group, from every stratum. That's a stratified sample. Stratified sample occurs when you take some representation of a bunch of different groups that you created before you started sampling. Going back to my biology example, suppose you're studying these ants and they live in a certain region of the forest. You might divide the forest up into 16 plots and then find 10 ants that live in each plot and use that as your stratified sample. Stratified samples might not be mathematically best, but they're certainly good, and they're often easier to pull off than a simple random sample. Next, we have what's called a cluster sample. Cluster sample is a sample chosen by dividing the population into groups, which we call clusters, and then selecting entire groups. If you're reading the definitions word for word, you can see that a stratified sample and a cluster sample are different. But when you're looking at an example and trying to determine whether it's stratified or cluster, it can be kind of subtle. The difference in the two is that in a cluster sample, you select entire groups and leave other groups completely out. And in a stratified sample, you select a few individuals from every group. Every group is guaranteed to get some sort of representation. So in a cluster sample, you might have, let's take like Colorado, which I can kind of draw because it's nice and rectangular, right? Now I have no idea what the breakdown of the counties in Colorado is, so I'm just going to draw a bunch of blobs here, right? Done, and you didn't have to watch me draw the whole thing. Suppose we want to do a survey of the post offices in Colorado. Rather than randomly selecting from all of these, which would be a stratified sample, a cluster sample would say randomly identify some of the counties. Again, what I'm doing here is haphazard, not random, but suppose this county got selected, and this county, and this one, and this one. We're going to randomly select 4 counties. The post office in those 4 counties would be included in the sample, and all of the post office outside of those counties would not be included. That's what makes this a cluster sample. In a stratified sample, we might have selected a few from each, but in a cluster sample, you take entire clusters and only include the individuals inside those clusters. That's the difference. Cluster samples can also be good because there's a probability involved because of the randomness in selecting clusters. But again, you have the same issue that not all possible groups of the same size have an equal chance of being chosen. It turns out that in a cluster sample, it's usually the case that each individual has the same chance of being selected because each cluster has the same chance of being selected. But it's not the case that all samples of the same size have the same chance of being selected. So these aren't mathematically perfect, but they're often easier to pull off than simple random samples. One more that depends on probability. A systematic sample is chosen by randomly selecting a starting point and then selecting every kth individual until the desired sample size is reached. So this ordinal here, this kth, I want you to treat that k like it's a variable and just imagine putting a number in there. So a systematic sample might say choose k equals 10, and we're going to take every 10th individual after some randomly selected starting point. Or maybe k is 25, and you're going to take every 25th individual. Or maybe k is 1,000, and you're going to take every 1,000th individual. So in a systematic sample, we pick some starting point, and then from there, we systematically choose objects to be in our sample. There are 2 ways I like to envision this. One is that you've got like a list of the elements in the population, right? So you've got this list, and maybe you randomly select a starting point right here, and then you say you're going to take every third. So 1, 2, skip those, take this one, 1, go to the next page, 2, 3, take this one, 1, 2, third, take this one, and so on until you get as many objects as you want. Another way I like to envision this is with objects going by on a conveyor belt. So here's my conveyor belt. We're going to do some sort of quality assurance inspection, maybe on candy bars. And you can see that I'm not much of an artist by my rendition of these lists over here, so I'm not even going to try to draw candy bars. I'm just going to write C for candy. And let's suppose we've employed some random process, and the first one we were supposed to test was this one, and after that we're going to choose every 5th. So this one goes by, this one goes by, this one goes by, we're going to select this one. And then we'll select this one, and this one, 5th, 1, 2, 3, 4, and so on until we get as many candy bars as we've been asked to test. How do you come up with the number that you wait between? Well, that might depend on how many you have or how long you want to take to gather your sample. Maybe you want to space it out more in the candy bar example. If you take every 5th, well, those are going to be probably made in a very similar way because they're so close to one another. Maybe we would want to space that out a little bit and test every 200th candy bar, but I didn't want you to have to watch me draw 200 candy bars on the screen, and so I chose a much smaller number. Systematic samples can be nice, especially outside of statistics, just from the perspective of quality assurance, right? Giving you these big gaps between is probably a good idea. But from a mathematical perspective, they're not best because it doesn't give every sample of the same size an equal chance of being selected. This method in the candy bar example gives no chance for 2 consecutive candy bars to be in the sample together. Now again, from a practical perspective, is that bad for quality assurance? Probably not. That's probably better that you're not taking 2 consecutive candy bars. But from a math perspective, we want all of the samples to have the same chance of being selected because it makes the math easier. We don't have to account for the fact that these samples have different probabilities of being selected, and so that's better from a math perspective. Now, in other texts, you'll see these first 4 methods called probability samples in general because they all have some sort of randomness involved. There are other methods for gathering samples which do not use randomness, and it's not that they don't have their place, but from a mathematical perspective, these are bad. We call these biased sampling methods because the method itself often yields biased results. The one that's mentioned in your book is what's called a convenience sample. A convenience sample is a sample comprised of elements who were selected because they were easily accessible. In a convenience sample, there's no randomness involved. The person doing the study just chooses individuals who are easy to get to. So if the person doing the study simply just approaches their friends or maybe their coworkers to get their data, rather than doing some sort of random selection, then they've created a convenience sample. And a convenience sample is going to be a biased sample because the very fact that they were convenient in some way probably means that they have something in common. Now that's not always true, but in general, friend groups will have lots of things in common and those results might not be a true reflection of the entire population. That's really what we're looking for here. We're looking for representation of the entire population in our samples. And if you've got a convenience sample, you've probably got some segment of that population. Because they were convenient, they probably had something in common, and that's what makes them easy to get to. My favorite example of this actually comes from my life. My junior high science fair project was determining whether individuals' blood pressure increased when they played video games. And I didn't go out and randomly select from the individuals in my town. I just got a bunch of my dork friends to come over and play Super Mario Bros. 2 for 10 minutes, and I tested their blood pressure before and after. Well, me and my dork friends played video games all the time, right? That we all had something in common. So in my data, I didn't detect any major change in blood pressure. Because again, this was common behavior. This is just something we always did. If I had done something with a little more randomness in it, and selected from maybe my entire class or the entire town, maybe I would have gotten different results. But because I selected from my friends, I created a biased sample. I couldn't have done any of those random things anyway. What was I going to do, talk to girls or strangers? What would I have done if I had randomly chosen a girl from my class that I had a crush on? Or if I had chosen a stranger in the phone book? I wasn't even allowed to talk to strangers. So a convenience sample was really all I could do there. But nowadays I look back in mathematical shame at my poor sampling method. This last one is not actually in your book, but it's so prevalent in modern society that I like to include it. It's called a volunteer sample. A volunteer sample is a sample comprised of elements who choose to contribute their data on their own initiative as opposed to being selected. In a volunteer sample, the method for gathering the data simply exists. And the person gathering the data doesn't actually select anybody, but rather allows others to self-select for the study. So for example, if you go to a restaurant with comment cards at every single table, you weren't randomly selected to get a comment card. That comment card is just sitting there, waiting for you, and if you choose to fill it out, great. But you have to make that choice. You weren't selected, you are selecting yourself. You're contributing data on your own initiative. And in that restaurant example, the people who fill out comment cards are not going to be representative of the entire population. Not everybody's willing to take the time to fill out a comment card, and a lot of the people who do might have a very strong opinion. Maybe they had a bad experience. And that's not that you can't get good information from it. If the same server's constantly getting bad feedback on the comment cards, well, that tells the manager or the owner of the restaurant that maybe something's up. But from a statistical standpoint, you're not getting an accurate representation of the entire population. Because there might be a lot of people who had very good service and didn't fill one out. There might also be people who had bad service and simply chose not to fill one out because they're non-confrontational. You're not getting a good representation of the entire population. From a statistical standpoint, that's bad. The reason I say that these are prevalent nowadays is not because of restaurants, though. It's because of the internet. When a web page or an internet site uses a survey on its page, that's probably a volunteer sample. You're not required to fill in the information. You're simply given the option to. So they leave the survey sitting there, and then you have the option to fill it out. There are many websites that cater to a specific type of person, and then that website might have a survey on it, and then they'll come back and say 86% of all Americans have this opinion, when in fact it's just 86% of the people who saw the survey on this website and chose to contribute their data have this opinion. There's a big difference between those two things. I'm not trying to turn you into a total cynic and have you doubt every single statistic that you hear. But if there's one thing I hope you get out of this class, it's that you should always ask, how was the data gathered? Because that matters. Quick recap of our sampling methods, and then we're going to go through some examples. First, a simple random sample is a sample where each group has the same exact chance of being selected. A stratified sample is a sample where you break up the population and then take a few individuals from each of those subdivisions, from each stratum. A cluster sample is a sample where you divide up the population but then select entire clusters, entire groups. A systematic sample is created by first choosing some element at random and then selecting every kth element from then on. A convenient sample is a sample where you just select individuals who are easy to get to. And a volunteer sample is a sample where you don't choose anybody, but rather you put something out there and then people choose to contribute their data. Let's go through some examples. A plant estimates the mean shearing strength of the bolts it produces by randomly selecting a bolt and then testing every 50th bolt until they reach 300 bolts tested. So I can picture these bolts going by on some sort of conveyor belt or something like that. And they're going to randomly select one, and then they're going to take every 50th. So K is 50. I'm kind of alluding to what this is. This is going to be a systematic sample. A website gathers opinions on a governmental policy by placing a survey on its main page. This is the one that we were just talking about. They're not choosing individuals to randomly give this to. They're just putting something out there and waiting for people to volunteer their data. This is a volunteer sample. Now you might argue that that seems like a convenient way to get data. A convenient sample is done by selecting individuals who are convenient. A volunteer sample, there's no selection made at all. The survey or whatever it happens to be simply exists, and then individuals run into it and choose to contribute their data. They aren't chosen, they self-select. Next example. A sample of professors at a university is selected by dividing the population by department and then randomly selecting 2 professors from each department. This is a subdivision of the population, and that should lead you to think of one of 2 options. This is either stratified or cluster. How do you tell the difference? In a stratified sample, you take a few individuals from each of the subdivisions, and in a cluster sample, you take entire subdivisions. So here it says they're taking 2 professors from each department, which makes this stratified. If it was a cluster sample, they might have divided up the entire population and then randomly selected and maybe gotten the history department and the math department, and those would be the 2 that contribute their data. But what they did here is they got a little bit of representation from each by choosing to employ a stratified sample. A sample of minor league baseball players is selected by randomly choosing 5 minor league teams and then surveying every player on the chosen squads. Notice that they're not choosing individuals from each team, but they're choosing entire teams. The population was broken up by team, and then they chose entire teams. That is a cluster sample. I know the difference is subtle, but you just got to ask this question. Did they take a few individuals from each subgroup? Or did they take every individual from a few subgroups? If they took a few individuals from each subgroup, that's stratified, and if they took everyone from a few subgroups, that's cluster. Next example. A math teacher surveys the students that come to his office hours about their feelings on taking college-level courses online. Right? Suppose this is how I wanted to gather data. I just waited for office hours and only took the students who showed up to office hours. In this case, I'm choosing the students. I found a frame by which I'm going to choose students. I'm going to choose students who show up to my office hours. So I'm making the choice, but it's not random in any way. In fact, they're just easy to get to because they show up to an office hour and then I just throw out the question, hey, that'd be a convenience sample. There's a very good chance that the data that I get from that would be biased in some way. It would not reflect the opinions of all of my students. Last one. A sample of members of the House of Representatives is selected by enumerating all members and then choosing 15 of them with a random number generator. So we're not dividing the population up into subgroups in any way. We're giving every individual a number and then just selecting from everybody. As long as that selection is done randomly, like with a random number generator, that's a simple random sample. Mathematically, these are best, and that's going to lead to our last slide, which again is so important that I put this in red. Because it makes the math easier, we're going to assume that all samples in our book are simple random samples when we get into the math portion of the course. So by the time we have to start worrying about how the data was gathered, we're just going to have this underlying assumption that all samples are simple random samples. That makes the math a lot easier. The methods that are in our book all assume that a simple random sample was used. If you don't use a simple random sample, the math can be much more complicated, and those techniques aren't in our book. We're only going to learn the methods for simple random samples, and that will be our underlying assumption. And that might make you wonder why we talked at all about any of these other sampling methods. Well, in my opinion, this is one of the few math classes you've ever taken in your life where you might actually use this stuff in the real world. I'm guessing you haven't used the quadratic formula very often in everyday life, nor have you had to use side angle side to prove that two triangles were congruent. But understanding that different sampling methods exist, using that knowledge to at least be aware that it's worthwhile to question how data was gathered, that's real world stuff. That's something you might want to be able to do. In this age of information, or possibly this age of misinformation, those are things you want to think about when you're reading an article or having a discussion. I hope you found something of interest in this section. As always, if you have any questions, send me an email or see me in an office hour.